So let's talk about a term that secretly runs our world in ways you probably never even think about: load analysis. It sounds a little dry, I know, but trust me, this one idea connects some wildly different fields, and getting a handle on it is kind of key to understanding how our modern world is built, managed, and kept safe. All right, let's kick things off with a little bit of a riddle. What on earth could possibly connect the massive churning blades of a wind turbine, a huge, power-hungry data center, and, of all things, a backyard trampoline? It sounds totally random, right? But the answer gets right to the heart of what we're talking about today. Okay, so first up, you've got the world of structural engineering. Think about the incredible physical forces at play on a bridge during rush hour, the constant stress on an airplane's wings, or just the sheer weight a skyscraper has to deal with every single day. This is load analysis in its most obvious tangible form, predicting and managing physical stress and strain.
But then you jump into a totally different, invisible world: electrical engineering. Here, load isn't a physical weight you can feel, it's the demand for electricity on the power grid. It's all about managing the invisible flow of energy that, well, powers pretty much everything in our lives. And now for the curveball: biomechanics. Believe it or not, the dynamic forces that an athlete puts on a trampoline with every bounce, that's also a form of load. It's all about understanding the stress on the human body and how it interacts with equipment. And that is our unifying answer: load.
So this is the big idea that ties it all together. Load analysis is basically the science of figuring out all the forces, stresses, or demands being put on any kind of system. And the goal is always the same, whether you're talking about a bridge or a power grid: make sure it works safely and make sure it works efficiently. All right, let's dive into the physical world first, the kinds of loads that we can really see and feel. This is the classic stuff: stress and strain, where engineers analyze the forces that could make something bend, buckle, or even break. And just think about all the forces at play here. You've got the immense pressure that could buckle a giant steel beam, or how load gets shared between a bunch of bolts holding a panel on. Then there's the intense centrifugal force on a motor spinning thousands of times a minute. It even gets down to the stress on these high-tech adhesive patches they use to repair aircraft, and, yep, back to the impact forces an athlete creates on a trampoline. It's all about physical pressure. And here's really the bottom line for physical loads. This whole analysis is about one thing: safety and reliability. Engineers are doing all these incredibly complex calculations for one simple reason: to predict and prevent a catastrophic failure long before it even has a chance of happening. Okay, so we've covered the tangible world of physical stress. Now let's switch gears and move into the more abstract stuff: the invisible loads, the world of demand and workload. It's just as critical. The language here changes, but the core idea is exactly the same. It's like a direct translation. The physical stress on a beam becomes the electrical demand on a grid. Force translates into capacity. And the risk of a structure buckling under pressure? Well, that's a lot like the workload on a team of employees. It's the same concept, just applied in a totally different way. And you see these abstract loads playing out everywhere. In our power systems, analysts are constantly measuring electrical demand to try and forecast how much we'll use and, prevent blackouts. In architecture, they calculate the cooling load for a new building. That's everything from sunlight to body heat to make sure the AC can handle it. And in factories, they use workload analysis to measure every single task, making sure they have exactly the right number of people to get the job done without burning everyone out. So you see the big difference, right? Where physical load analysis is often about preventing catastrophic failure, abstract load analysis is all about optimization. The goal isn't just to keep the system from breaking down, it's to make it run as smoothly, efficiently, and cost-effectively as humanly possible. So for decades, these two worlds, the physical and the abstract, were analyzed with completely different sets of tools. But that's all changing. Right now, a powerful new toolkit is coming into its own, and it's unifying everything. And yeah, you guessed it, it's driven by AI. We're talking about some seriously powerful computational methods. For physical things, you've got something called finite element analysis, FEA, which breaks down complex objects into millions of tiny little pieces to simulate stress. And for abstract data, we have this whole suite of machine learning tools, things like artificial neural networks and LSTMs, which are just brilliant at spotting complex, hidden patterns in data, whether it's energy usage or material fatigue. And this is where it all just clicks into place. I mean, look at this. The same family of computational tools is being used to solve all these different problems.
The methods used to predict when a structural beam might fail are conceptually related to the AI used to forecast a city's energy needs, or the neural nets that predict forces in manufacturing. It's becoming a universal language for prediction.
And these new methods aren't just a tiny improvement, they're a massive leap forward. This chart, for instance, shows how accurate different models are at forecasting electrical load. Traditional stats are pretty good, but when you apply an advanced AI, like a long short-term memory network, which is literally designed to see patterns over time, the accuracy just skyrockets. And that better prediction translates directly into a more stable and efficient power grid for all of us. So, we've gone from bridges to power grids, we've seen how AI is starting to tie it all together. But what's the big picture? Why does any of this really matter in the real world? Well, when you boil it all down, understanding loads is just fundamental to how we live. It's what ensures our bridges and airplanes are safe. It's what boosts the efficiency of our factories and power grids, which saves money and resources. It drives innovation, pushing us to create stronger, lighter materials and smarter self-regulating systems. It is the invisible science behind the reliability we all depend on every single day. Which leaves us with a final big question to think about. We're getting incredibly good at predicting physical stress and system demand. But as our world gets more and more interconnected, as everything from our cars to our power grids gets smarter, what do you think is the next great frontier for load analysis? What's the next critical load we'll need to learn how to predict?